1953. A young scientist in a lab at Caltech is trying to measure the age of the Earth. Over and over the numbers come out wrong. So he starts digging, and what he finds stops him cold. One particular metal is everywhere, in the air, in the water, in the walls, in people's blood, in amounts that should never have been there in the entire history of the planet. That discovery cost him his peace of mind, because behind that metal stood a lot of very powerful money. But let's start from the beginning, because the story of this dull, gray, unremarkable metal is the story of how empires collapse, how entire generations lose their minds, and how one man, standing alone against an industrial machine, turned out to be right. And it doesn't begin on Earth. It begins in space. At the moment, two dead stars collide. Humanity has been carrying this metal through its entire history, drinking it with wine, breathing it in at every city intersection, painting it onto the walls of children's bedrooms. Did people not know what they were doing? Some did. Money just mattered more. This is the story of lead, how it's born in cosmic disasters, how it brings down empires and permanently rewires entire generations of people, and how one man with a notebook and a clean room managed to put a stop to it, even as everyone around him told him to shut up. Lead is element number 82, gray, heavy, and so soft you can scratch it with your fingernail. It doesn't shine, doesn't burn, barely reacts with anything. It looks like a metal nature is embarrassed by. And yet, it's exactly where entire families of radioactive elements come to die. It's the energy dead end for certain decay chains. Once an atomic nucleus works its way down to lead's configuration through those chains, there's no way back. The protons and neutrons have settled to the bottom, and there they stay, permanently at rest. We tend to think of gold as the ultimate prize. Alchemists spent centuries trying to turn anything they could find into that yellow gleam. But nature has no interest in our aesthetic preferences. It doesn't make gold the final destination of decay chains. It makes lead. Dull, unattractive, toxic, and extraordinarily stable. A graveyard for atoms. The last stop for entire families of heavy radioactive elements. And this is where the story turns genuinely dark. Because this metal, the very endpoint of nuclear decay, is the one humanity managed to put to work everywhere. We poured it into pipes. We mixed it into food. We added it to paint. We burned it in engines. We lived with it for thousands of years without understanding that we were slowly building ourselves a coffin from the same material that nature tucks away at the very bottom of its storage. But let's go back to the beginning. Where did lead actually come from? Lead doesn't form in ordinary stars. That's important to understand right away. Our sun is a nuclear fusion reactor where hydrogen burns and becomes helium. Helium becomes carbon. Carbon becomes oxygen. This works well up to about iron, element number 26. After that, fusion stops making sense. To build something heavier than iron, you have to put energy in rather than get it out. An ordinary star simply can't afford that. It stops at iron. For lead, you need something different. You need a catastrophe. For a long time, scientists believed that supernova explosions were the main source of heavy elements. When a star 8, 10, or 20 times more massive than our sun reaches the end of its life, it doesn't fade quietly. It collapses in a fraction of a second and then explodes with such force that for weeks it outshines an entire galaxy of hundreds of billions of stars. In the moment of the explosion, a massive flood of neutrons bombards atomic nuclei so rapidly that the nuclei don't have time to decay. They just keep absorbing neutrons one after another, growing heavier and heavier, and through a series of subsequent decays, they transform into heavy elements. Then, in 2017, something happened that turned this picture upside down. Astronomers detected the collision of two neutron stars, the dead cores left behind by long-extinct giants. The event was labeled GW170817. It was picked up simultaneously by gravitational wave detectors and by optical telescopes, the first time in the history of science that a single cosmic event had been observed with two fundamentally different methods at once. Spectral analysis revealed that in this merger, Within a fraction of a second, enormous quantities of heavy elements had formed, including gold, platinum, and lead. This showed that neutron star mergers are one of the primary sources, perhaps the primary source, of heavy elements in the universe. The question is still being studied, and the debate continues. But GW170817 fundamentally changed our understanding of where heavy matter is forged. The mechanism is called the R process, where R stands for rapid neutron capture. Rapid because nuclei absorb neutrons faster than they can decay. This is what produced most of the lead in Earth's crust. There's also the S process, the slow neutron capture process, which takes place deep inside red giants, stars in the final stage of their lives. It produces lead too, but different isotopes and in smaller quantities. If the R process is a catastrophe, two dead stellar cores slamming into each other in a single instant, then the S process is a long, slow simmering inside the dying furnace of a fading giant, stretched out over millions of years. So every piece of lead you've ever seen, in fishing weights, in car batteries, in old pipes, is literally a fragment of someone else's disaster. Two neutron stars flew toward each other for billions of years. They collided. They exploded outward in a cloud of white-hot matter into space. That cloud, mixed with interstellar gas, collapsed under its own gravity and gave birth to our solar system roughly 4.6 billion years ago. Lead settled into rock, rock clumped into a planet, the planet cooled, and then we showed up and started smelting it. We are literally building plumbing out of the wreckage of stellar collisions. That's not a metaphor. That's the actual history of every atom in this metal. Now, how did humanity first find this metal? And why couldn't it let go? Lead is one of the very first metals humans ever learned to smelt. That's no accident. The main ore it comes from, galena, which is lead sulfide, is found all over the world and is easy to recognize without any specialized knowledge. Heavy, shiny, cubic crystals of silvery gray, surprisingly dense for their size. Smelting lead from galena isn't technically difficult. The metal melts at just 327 degrees Celsius, which is achievable in an open fire with decent airflow. Ancient metal workers were essentially getting lead by accident when they roasted the ore in campfires, watching a heavy, shiny liquid pour out of the rock. The oldest evidence of deliberate lead smelting dates back to around the 7th millennium before the Common Era, with archaeological finds in what is now Turkey and Israel. That's 9,000 years ago. Lead is older than bronze, older than iron, one of the earliest metals in the human story and one of the longest continuously used. Why did ancient people take to it so quickly? Because it's easy to work with. It melts in a simple hearth. It's soft enough to cut with a knife, bend with your hands, shape into anything without complicated tools. It doesn't rust or degrade over time. Lead objects buried for 2,000 years look almost the same as the day they were made. It's heavy, which made it perfect for weights, anchors, and counterbalances. And there was plenty of it. Galena is found on every continent, and mining it required no advanced technology. The first large-scale mines appeared in several places at roughly the same time, in what is now Spain, Greece, Britain, and Asia Minor. The Spanish deposits near Cartagena were already being worked by Phoenician traders long before the Romans arrived. When Rome conquered the Iberian Peninsula, it found a fully developed mining infrastructure waiting for it, and immediately put it on an industrial footing. At the height of the Roman Empire, Spanish mines were producing tens of thousands of tons of lead per year. Various estimates put total Roman lead production at around 80,000 tons annually, a figure Europe would not surpass again until the Industrial Revolution. The work was done by slaves, under conditions that can only be described one way: slow destruction. Mining galena wasn't just brutal physical labor in cramped darkness. It meant constantly breathing in lead dust and sulfur dioxide fumes released during roasting, in poorly ventilated underground passages. The concentration of lead in the air of those mines was such that workers rarely survived more than a few years. Everyone knew this. Nobody considered it a problem. There were enough slaves. The scale of Roman lead production was so enormous that its traces have been found in ice cores from Greenland, the very same cores that Patterson would study 2,000 years later. In the layers of ice corresponding to the height of the Roman Empire, roughly from the 2nd century before the Common Era to the 2nd century of the Common Era, lead levels in the atmosphere are measurably higher than the natural background. This was the first industrial pollution of the planet's atmosphere by a heavy metal in all of human history. Rome literally left its chemical signature in the Arctic ice, and that signature is still readable 20 centuries later. After the fall of the Western Roman Empire in the 5th century, lead production in Europe dropped sharply. In the ice cores, this is completely clear. Lead levels in the atmosphere fall back toward the natural background. Medieval Europe rebuilt its mining capacity slowly. The largest medieval mines operated in Germany, especially in the Harz and Ore mountain regions, in England, in Derbyshire and Yorkshire, and in Bohemia. Lead went into cathedral roofs and monastery coverings. Into the lead came that holds stained glass windows in place to this day, into weights for fishing nets, and into tableware for wealthy households. Medieval craftsmen, roofers, solderers, and glassworkers worked with molten metal constantly, and slowly accumulated in their bones what nature had sent to Earth from the cores of dead stars. Now, alchemy. Because here lies one of the strangest and most revealing turns in this entire story. In the alchemical tradition, lead held an absolutely unique place, not simply as one of the metals, but as a symbol of the beginning of everything, the starting point of the great work. Alchemists matched each of the 7 metals known to them with one of the 7 planets visible to the naked eye. Gold was the sun, silver the moon, copper Venus, iron Mars, Mercury, tin Jupiter, and lead was Saturn. The slowest of the visible planets in the ancient world, the most distant, the darkest, linked in mythology to time, to limitation, to the heaviness of existence. It's no coincidence that chronic lead poisoning is still medically called Saturnism to this day. In this system, lead was considered the lowest of metals, heavy, inert, dark, without luster, the complete opposite of gold. But that was precisely why it served as the starting point of the great work. Alchemists developed a theory that all metals in nature slowly ripen within the earth, striving to become gold, the most perfect of metals. In this worldview, lead was the unripe, imperfect metal that had not yet completed the long journey of natural maturation. The alchemist's task was to accelerate this process artificially, using the philosopher's stone or other means of transmutation. And you had to start from the very lowest, from lead. There's a bitter irony here that the alchemists couldn't possibly have suspected. They intuitively grasped something real, but got the direction completely backwards. In nature, it isn't lead that strives to become gold. In nature, it's exactly the other way around. Radioactive elements heavier than both gold and lead, uranium, thorium, radium, slowly decay and ultimately arrive at lead. Nature doesn't move upward through some imagined hierarchy of metals toward gold. It moves downward, toward stability, toward stillness, toward lead. The alchemists were looking in the right direction when they described metals moving toward a final destination. But the final destination wasn't gold, it was lead. Working with lead was perfectly routine in an alchemical laboratory. It was melted in crucibles, dissolved in vinegar, heated over fire, mixed with sulfur and salts. Lead acetate, the sweet-tasting substance the Romans added to wine, was well known to alchemists under the name sugar of Saturn. Some of them tasted substances as a standard method of identification, which was normal practice in chemical analysis right up to the 19th century. That this was slowly killing them was something they naturally did not know. The famous physician and alchemist Paracelsus, who lived in the 16th century and is considered one of the founders of toxicology and pharmacology, worked extensively with lead compounds and described their properties in detail. He was the one who formulated the principle that became the foundation of modern toxicology. All things are poison, and nothing is without poison. Only the dose makes a thing not a poison. That principle holds true today. The bitter irony is that Paracelsus himself was almost certainly experiencing chronic lead exposure throughout decades of laboratory practice. Alchemy never turned lead into gold, but it became the mother of chemistry. The very techniques for working with metals and their compounds that alchemists refined over centuries — distillation, dissolution, precipitation, calcination — became the foundation of modern analytical chemistry. The same chemistry that Patterson would use to measure trace quantities of lead in ice samples and meteorites. The circle closed. Medieval alchemists worked with lead in pursuit of the secrets of matter, and their methods ultimately helped prove that this metal had poisoned the atmosphere of the entire planet. Now, the version most of us were taught in school. It goes something like this. Lead is stable, inert, shields against radiation, melts at 327 degrees Celsius, and is easy to work with as a result. All of that is true, but it's not the whole truth, and in this particular case, incomplete truth kills. Your body is not a physicist, not a chemist. It's a set of biological programs that were written over billions of years in a world where lead in any dissolved, accessible form was essentially absent. Evolution never seriously had to deal with this specific problem, and we have no defenses against it whatsoever. Lead ions are very similar in size and charge to calcium ions. Calcium is the building material of your bones and one of the key signaling elements in neurons. It regulates the transmission of nerve impulses, muscle contractions, and hormone secretion. When lead enters the bloodstream, the cellular transport systems mistake it for calcium, and they start pumping it inside. Lead gets built into bones in place of calcium. It penetrates neurons, but it behaves in a completely different way, disrupting the function of enzymes, interfering with protein synthesis, and altering the electrical potentials across cell membranes. The brain starts working differently, slower, more chaotically. Some neural connections die with no possibility of recovery. This is not theory or speculation. It is a measured, documented, reproducible fact. Research by neurotoxicologist Herbert Needleman at the University of Pittsburgh, published in 1979 in the New England Journal of Medicine and considered foundational in this field, demonstrated a direct link between blood lead levels in children and declining cognitive performance. Each additional microgram of lead per deciliter of blood in a child is associated with a drop in IQ of roughly 1 to 2 points on average. In children, during the critical window of brain development, this effect is permanent. A brain damaged by lead in childhood does not recover in adulthood. The obvious question is, if this is known, why did it take us so long to notice? Because lead was too convenient. Soft, easy to melt, rust-proof, resistant to most acids. It was the perfect technical metal for a civilization that had no plastics and no stainless steel. So it went into everything, and no one wanted to acknowledge the problem, especially those who were profiting from it. Rome. This is where the story becomes genuinely disturbing. Romans used lead everywhere. The English word plumbing comes directly from the Latin word plumbum, meaning lead. That's a straight line from Roman water systems to modern pipes. But the pipes weren't even the worst of it. There was another invention, far more insidious. Sapa. That was the name of a substance Roman cooks and winemakers produced in enormous quantities. The method was simple. Take sour wine or grape juice, boil it down in a lead pot, and you get a thick, sweet syrup. The sweetness has a chemical explanation. The acetic acid in sour wine reacts with lead and forms lead acetate. This compound genuinely tastes sweet. It was literally called sugar of lead and used exactly as a sweetener. Added to wine, to sauces, to confections, it was a cheap and accessible way to make sour wine pleasant in an era when cane sugar was a luxury available to almost no one. Canadian toxicologist Jerome Noriega, who published a detailed analysis of this problem in 1983 in the New England Journal of Medicine, estimated that the concentration of lead acetate in Sapa could reach several hundred milligrams per liter. At regular consumption, that's a dose sufficient to produce sustained chronic poisoning. Now consider the symptoms of lead poisoning: chronic fatigue, gout, male infertility, memory problems, dramatic mood swings, impulsive behavior, weakness in the limbs. This is the clinical picture of Saturnism, the medical term for lead poisoning, named after the Latin word for lead. Now read the historical accounts of the illnesses that afflicted Roman emperors. Nero's impulsiveness and cruelty that went beyond any rational limit. Caligula's documented neurological episodes and erratic behavior. Claudius's tremors and speech difficulties, described in detail by his contemporaries. This isn't an attempt to diagnose people across 2,000 years. It's a statistical pattern that lines up with the clinical signs of chronic heavy metal poisoning. A necessary caveat. The idea that lead killed Rome is a hypothesis, not an established historical fact. Historians have debated this for a long time, and they continue to do so. Rome fell for a whole range of reasons: political crisis, pressure on the borders, economic problems, plagues. But what no one disputes is this: Rome's ruling elite was systematically consuming lead in quantities well sufficient to cause chronic poisoning. And the symptoms described in historical sources match what we see in clinical descriptions of Saturnism. That is not a coincidence. That is toxicology. While the legions held the Rhine and the Danube, defending the frontiers of a vast empire, Rome's elite was drinking wine sweetened with lead acetate and slowly losing the capacity to make sound decisions. The empire was rotting from the inside, literally in the chemical sense of the word. Fast forward 20 centuries. 1953, California Institute of Technology, Pasadena. A young geochemist named Clair Patterson is working on what seems like a purely technical calculation. He needs to determine the age of the Earth from the isotopic composition of lead in meteorites. The logic is straightforward. Uranium decays into lead at a known, precisely measured rate. So if you measure the ratio of uranium to lead isotopes in ancient samples, you can calculate how long that decay has been going on, which gives you the age of the material, which gives you the age of the Earth. Clear enough. But the numbers wouldn't line up. Over and over, Patterson was getting results showing anomalously high levels of lead, far more than should be there from uranium decay alone. Where was the extra lead coming from? Patterson was meticulous to a degree that bordered on obsession. He didn't chalk it up to measurement error and move on. He dug. And what he found was staggering in its scale. His laboratory was contaminated with lead. Not because anyone had spilled something. Lead was simply everywhere, in the air, on the walls, on the hands of lab assistants, in the reagents, in the distilled water. It was settling onto samples directly from the atmosphere. The atmosphere was so saturated with lead that it showed up as background noise in any room, on any surface. To continue his work, Patterson did something no scientist had done before. He built the world's first clean room, a sealed space with air filtered many times over, where every surface was specially treated and every reagent purified to a degree of cleanliness that had previously been considered unachievable. At the time, it seemed like technological madness. His colleagues thought he'd lost the plot. But it was the only way to get uncontaminated data, and in 1956, Patterson published his result. The age of the Earth is approximately 4.55 billion years. That figure, with minor refinements, is still accepted today. He had solved a problem that several generations of scientists had struggled with. That alone would have been a sufficient lifetime achievement. But along the way, he discovered something else. Something that wouldn't leave him alone and ultimately redirected the rest of his career entirely. Patterson began studying lead concentrations in different layers of Arctic and Antarctic ice. Ice is a natural archive. Every year, snow falls and captures particles from the atmosphere. The snow compacts into ice, and in a vertical cross-section of a glacier, you can read the history of the air like an open book. Patterson took samples from layers corresponding to different historical periods and measured their lead concentrations with the extraordinary precision he himself had developed. What he saw shook him so deeply that he changed the direction of his scientific work entirely. Up until roughly the 1920s and 30s, lead levels in the atmosphere were minimal, close to the natural background. And then, a vertical spike, nearly a straight line going up, coinciding precisely in time with one single specific event in the industrial history of humanity. The introduction of leaded gasoline, Thomas Midgley Jr. Most people don't know that name. They should. Historian John McNeill wrote that Midgley had more impact on the atmosphere than any other single organism in the history of Earth. That is not a compliment. It is a verdict. In the early 1920s, car engines suffered from a common and deeply irritating problem: engine knock. The fuel-air mixture would ignite at the wrong moment in the cylinder. The engine would rattle, lose power, and wear out faster. What was needed was an additive that would make combustion smooth and predictable. Midgley, working in the research division of General Motors, found the answer: tetraethyl lead. This organic lead compound, added to gasoline in small quantities, a few grams per liter, almost completely eliminated engine knock. Cheap, effective, and scalable to industrial volumes. General Motors and Standard Oil formed a joint venture called the Ethyl Corporation and launched production in 1923. Even then, there were people who understood perfectly well that this was a bad idea. Lead had been known as a poison since ancient Greek and Roman times. Workers at the tetraethyl lead manufacturing plants were falling ill in large numbers. At the plant in Deepwater, New Jersey, in 1924, several workers died from acute tetraethyl lead poisoning, and dozens more suffered permanent neurological damage. Workers were hallucinating on the factory floor, behaving erratically, losing their bearings. Journalists covering these events nicknamed the building the Looney Gas Building. What did Midgley do? He held a press conference. Right in front of the cameras and reporters, he demonstratively washed his hands with tetraethyl lead. He declared he could do this every day without the slightest harm to his health. At the time of that press conference, he had recently been treated for lead poisoning himself. Quietly, behind closed doors, without any public disclosure. It is difficult to imagine that a man being treated for lead poisoning did not know what he was doing. But Midgley's story has a second chapter, and it is no less dark, because one man managed to alter the chemistry of the entire planet's atmosphere twice. After tetraethyl lead, Midgley turned to another industrial problem. The refrigerators of the time ran on genuinely dangerous coolants: ammonia, methyl chloride, sulfur dioxide. A leak in an enclosed space could mean poisoning or fire. The refrigeration industry desperately needed a safe alternative, something chemically inert, non-flammable, and non-toxic to humans. In 1930, Midgley and colleagues at General Motors synthesized the first chlorofluorocarbon, what would become known as Freon. It really was safe in direct contact with people. Non-flammable. Chemically inert under normal conditions. Odorless. At a demonstration for colleagues, Midgley inhaled Freon and breathed it out onto a candle flame, extinguishing it. The audience applauded. It seemed like he had this time solved the problem perfectly, with no side effects whatsoever. 40 years passed. In 1974, American chemists Mario Molina and Sherwood Rowland published a paper in Nature that changed everything. They showed that chlorofluorocarbon molecules are chemically inert in the lower atmosphere, but when they drift up into the stratosphere at altitudes of 20 to 25 kilometers, intense ultraviolet radiation breaks them apart. Chlorine atoms are released. These atoms trigger a chain reaction that destroys ozone, breaking apart molecules of O3 into O2 and a single oxygen atom. One chlorine atom can destroy up to 100,000 ozone molecules before it is finally neutralized by other substances. The ozone layer, which shields all life on Earth from harmful ultraviolet radiation, had begun thinning across the entire planet. In 1985, British scientists working at the Halley Research Station in Antarctica detected an ozone hole over the continent, a region where the ozone layer had thinned catastrophically by more than 40% compared to normal. The discovery stunned the scientific community. In 1987, the Montreal Protocol was signed, an international agreement to phase out the production and use of chlorofluorocarbons. It is one of the rare environmental treaties that actually worked. The ozone layer has been slowly recovering, and scientists project it will return to normal by the middle of the 21st century. In 1995, Molina and Rowland received the Nobel Prize in Chemistry. Thomas Midgley had died by then, in 1944, from a cause that is difficult to call anything other than cruel irony. In his final years, he was partially paralyzed from polio. Being an inventor by nature, he designed a system of pulleys, ropes, and counterweights to help himself get out of bed independently. In 1944, he became entangled in that system and died. He did not live to see the full scale of the ozone catastrophe, nor the moment the world finally abandoned his inventions. One man, two inventions. The first, tetraethyl lead, saturated the planet's atmosphere with lead for 7 decades and chemically altered the neurology of entire generations of people across the world. The second, freon, punched a hole in the ozone layer that protected all life on Earth from ultraviolet radiation. John McNeill was absolutely right. No other single organism in the history of Earth has had a more destructive impact on the atmosphere. And notably, both inventions looked at the time of their creation like brilliant technical solutions to real problems. The devil, as always, was hiding in the details that nobody bothered to check. Leaded gasoline was not banned in the United States until 1996. 73 years. Over those 7 decades, cars around the world burned millions of tons of tetraethyl lead fuel, and every vehicle pumped lead compounds directly into city air through its exhaust pipe. It settled into the soil along roads, washed into rivers and groundwater, entered the food supply through dust. It accumulated in the bones of everyone who lived during that period. The last country to officially ban leaded gasoline was Algeria in July 2021. Patterson saw all of this in his data, and he did not stay silent. He began publishing research on global lead contamination, testifying before congressional committees, and persistently pushing for legislative action. The response from the oil and automotive industries was predictable and aggressive. His research funding dried up. Oil companies hired scientists to publicly dispute his data and his methodology. The Ethyl Corporation and affiliated organizations ran a sustained campaign against Patterson for years, working to portray him as a crank who was seeing a problem where none existed. This was not paranoia or conspiracy thinking. It was documented corporate pressure against a scientist who had found an extremely inconvenient truth. But the data was solid. Patterson had developed techniques for measuring trace quantities of lead at the level of parts per trillion, essentially inventing modern analytical chemistry for working with ultra-low concentrations. That alone is a major independent scientific achievement, now used in hundreds of laboratories around the world. His data from ice cores taken in Greenland and Antarctica was irrefutable. Pre-industrial baseline, essentially zero. Early 20th century, rapid rise. The 1970s, peak levels. Then a decline as restrictions began to take effect. The history of the planet's atmosphere, written in ice, readable through lead. In 1970, the United States passed the Clean Air Act. Gradually, over the next 2 decades, leaded gasoline was banned first in the United States and then in most of the developed world. Patterson died in 1995. He never received the Nobel Prize. The man who determined the age of the Earth and effectively pulled millions of tons of lead out of the air walked past the most prestigious scientific award on the planet without collecting it. An unjust story, but entirely in the spirit of the metal we're talking about. Now, a story that flips sociology on its head, and one that most people still don't know. In the late 1990s and early 2000s, several independent researchers noticed a strange pattern. Violent crime in the United States had surged sharply from the late 1960s, peaked in the early 90s, and then dropped just as sharply and in lockstep across the entire country. Everywhere, simultaneously, in big cities and small ones, in wealthy neighborhoods and poor ones, in the North and the South. Sociologists and criminologists offered various explanations. Tougher sentencing laws, shifts in the demographic structure, the economic boom of the 90s. None of these explanations produced such a precise, synchronized, geographically uniform correlation across the whole country. Then, economist Jessica Wolpaw-Reyes of Amherst College, in a paper published in 2007, laid a completely different graph on top of the crime data. A graph showing the level of lead exposure experienced by children born in different years. The match was extraordinary. With one adjustment, a time lag of roughly 20 years. The peak in leaded gasoline use came in the 1960s and 70s. Children born during those years, growing up in cities with heavy traffic, were receiving elevated doses of lead during exactly the critical early window when the brain is most actively developing and most vulnerable. 20 years later, those children were adults. And that was precisely the moment when violent crime statistics began to climb. When leaded gasoline production started declining in the 1970s, the next generation of children received significantly less lead. 20 years after that, crime began to fall. A similar pattern played out in several other countries where leaded gasoline was banned at different times. In each country, the violent crime curve followed the lead curve with the same lag of roughly 2 decades. Why does lead affect behavior? Neuroscience offers a clear answer. Lead disrupts the development of the prefrontal cortex, the front part of the brain responsible for planning, impulse control, and the ability to think through consequences. This is the part of the brain that says, wait, think, don't do this. Lead prevents it from developing properly during childhood. A person whose prefrontal cortex was damaged in early life has a harder time controlling aggression, assessing risk, and managing frustration. An important and necessary caveat: correlation does not by itself prove causation. The scientific community continues to debate this hypothesis. Many researchers find the evidence compelling, while others point to methodological difficulties. Poverty, social environment, access to weapons, the quality of law enforcement, all of these also affect crime rates. But here is what remains a fact. No other single variable has produced such a precise temporal and geographic match, simultaneously, across multiple countries. We weren't just poisoning people's bodies. We were chemically altering the way their brains worked, without even realizing it. Millions of people around the world lived with nervous systems whose development had been disrupted by a metal drifting out of the exhaust pipe of a car driving past a playground. This is not conspiracy theory. These are publications in peer-reviewed scientific journals. There's a separate story in how lead actually works as a poison at the cellular level. Because the details here are unsettling even for people who know toxicology well. Lead blocks several key enzymes in the chain that produces heme, the molecule at the center of hemoglobin that carries oxygen from the lungs to the body's tissues. When that chain is disrupted, normal hemoglobin production drops and anemia develops. This is one of the earliest clinical signs of poisoning, which is why people with chronic lead exposure often show a characteristic pallor and constant fatigue. At the same time, lead attacks the kidneys. It accumulates in the renal tubules and gradually impairs their function, leading to what's called lead nephropathy. In prolonged chronic poisoning, this can progress to serious kidney failure. The nervous system is damaged along 2 separate tracks. In the central nervous system, lead disrupts the synthesis of neurotransmitters and damages the myelin sheaths around nerve fibers, which are responsible for the speed at which nerve signals travel. The peripheral nervous system shows a different and characteristic sign. One of the classic presentations of Saturnism is wrist drop, a weakness of the muscles that extend the hand, which simply can no longer be straightened normally. Painters in centuries past who worked daily with lead white paint, the most widely used white pigment right up to the 20th century, frequently suffered from exactly this. It was an occupational disease of the profession. And here is another fact that is genuinely uncomfortable. The half-life of lead in bone is around 27 years. That means lead absorbed during childhood will slowly and steadily leach back out of the bones into the bloodstream over the following several decades. For women, the most critical periods are pregnancy and menopause, when calcium is actively mobilized from bone tissue. Lead comes along with it, going straight into the bloodstream, and from a mother into her child across the placenta. In other words, the lead your mother absorbed as a small child playing near a busy road in the 1960s could have reached you, through her, before you were even born. Things are significantly better now. Blood lead levels in the populations of developed countries have dropped by 5 to 10 times compared to the 1970s. This is one of the most significant and underappreciated public health victories in history. Removing one poison from the air actually changed the biochemistry of entire national populations. Not an exaggeration, a measured and documented fact. But the problem has not disappeared entirely, not even close. In 2014, the American city of Flint, Michigan switched its water supply source to save money. The new water turned out to be significantly more corrosive in its chemical composition than the previous source. It began eating away at the old lead pipes in the city's water system, a legacy of the previous century. Lead began appearing in residents' taps, at concentrations many times above acceptable limits. Children in Flint developed chronic poisoning. City and state officials knew and concealed the information. The story came to light largely because of pediatrician Mona Hanna-Attisha, who persistently compared children's blood test results against archived data and refused to accept official assurances of safety. And researcher Mark Edwards of Virginia Tech, who conducted independent water testing from Flint taps in the face of active pressure from authorities. Flint is not an exception or an anomaly. According to American researchers, somewhere between 6 and 10 million homes in the United States are still connected to water systems that contain lead pipes or lead fittings. This is the direct legacy of the construction boom of the 19th and early 20th centuries. In developing countries, the situation is considerably worse. Lead is still used in paints and small-scale manufacturing, and batteries are smelted by informal recyclers right in residential neighborhoods, filling the air with lead fumes. The World Health Organization lists lead as one of the 10 chemicals of greatest public health concern on the planet. The official position of modern medicine is unambiguous. There is no safe level of lead in the blood. Any amount above zero already produces a measurable negative effect on the body, above all on the developing brains of children. And yet, here is where the irony reaches its absolute peak. We can't fully give up lead. Not now, not in the foreseeable future. Lead remains the best commercially available material for shielding against ionizing radiation. The reason lies in its high density, 11.3 grams per cubic centimeter, and its high atomic number. The heavy nuclei of lead atoms are extremely effective at absorbing gamma rays and X-rays, scattering their energy. To get equivalent shielding with concrete, you'd need a layer roughly 5 to 6 times thicker. That's why lead is in the protective aprons worn by radiologists and patients at dental offices, in the walls of X-ray rooms and CT scanning suites, in the shielding of nuclear reactors, in the containers used to transport and store radioactive materials and nuclear waste. We're protecting ourselves from one form of danger using another. The only affordable and available shield against gamma radiation is a metal that is a chronic neurotoxin. That's not a philosophical metaphor. That is the literal engineering reality of today. In medicine, lead is gradually being phased out. New lead-free shielding materials are emerging, based on barium, bismuth, tungsten, and their compounds. They work, and they provide adequate protection. But they cost more and are not yet accessible in much of the world. The transition is happening slowly. The lead-acid battery, the one in your car if it's not an electric vehicle, was invented in 1859 by French physicist Gaston Planté, and its basic operating principle hasn't changed since. It's cheap, reliable, performs well in cold temperatures, and can deliver a powerful burst of current in an instant. It is still manufactured at enormous industrial scale. Around 80% of these batteries are recycled and returned to the production cycle, one of the highest recycling rates of any industrial material. Not out of ecological conscience, simply because lead is valuable enough that recovering and reusing it makes economic sense. Cynical economics turning out to be an unlikely ally of the environment. Lead white paint. For nearly 2,000 years, from ancient Greece to the early 20th century, it was the dominant white pigment in both fine art and household paint. Lead carbonate ground with linseed oil produced a dense, opaque, beautiful white with excellent coverage. Every major master of European painting worked with it. Rubens, Rembrandt, Vermeer, Titian. The same pigment went into the paint on the walls of family homes. Artists worked with this pigment every day, for hours at a time. They ground it by hand, worked it on stone slabs, mixed it with oil. Lead dust settled on their hands, entered their mouths, was inhaled from the air. Francisco Goya, around the age of 46, suffered a severe illness. Sudden, profound hearing loss, balance disturbances, weakness, visual problems. His painting changed radically afterward. The famous black paintings appeared, dark, anxious, filled with shadow, strikingly different from his earlier work. Some researchers have proposed lead poisoning as one possible contributing factor in Goya's illness. This is not an established diagnosis. It is one hypothesis among several. But it doesn't look implausible against the backdrop of what we know about painters' long-term professional contact with lead pigments. According to the United States Centers for Disease Control and Prevention, between 1976 and 1980, approximately 88% of children aged 1 to 5 in the country had blood lead levels above 10 micrograms per deciliter. Almost every child in the country was chronically poisoned. Today, that figure has dropped to around 1%. This is a victory whose scale is hard to overstate, and one that almost never gets discussed publicly. Crystal glassware. The kind used to make beautiful wine glasses, vases, and decanters. Traditional lead crystal contains between 24 and 36% lead oxide by weight. That's precisely what makes the glass so heavy, so brilliantly refractive, and what produces that characteristic musical ring when it's lightly struck. Pour an acidic wine into a lead crystal glass and leave it for several hours, and the acid begins slowly dissolving lead oxide from the surface of the glass. In various laboratory experiments, lead leaching during prolonged contact with acidic drinks has exceeded recommended safety levels. One glass of wine at dinner is not a catastrophe, but wealthy people in centuries past often stored brandy or port in lead crystal decanters for months at a time. The dose that accumulated over such a period was far from negligible. Lead-free crystal is now produced using barium oxide or potassium oxide. Just as beautiful, simply without the lead. Bullets. Lead was chosen for ammunition production for specific reasons. Its density, 11.3 grams per cubic centimeter, is almost 1.5 times greater than that of iron. At the same diameter, a lead bullet is heavier, which means at the same initial velocity, it carries more kinetic energy and loses it more slowly in flight. The California condor, a bird that was once on the very brink of extinction, suffered significantly because of lead ammunition. These scavengers feed on the internal organs of animals killed by hunters. The carcasses contained small fragments of lead bullets. The condors swallowed them and died of poisoning. This led to a legislative ban on lead ammunition for hunting in California. Geochronology, the science of determining the age of rocks, is in many ways built on lead. Uranium-238 decays into lead-206 with a half-life of 4.47 billion years. Uranium-235 decays into lead-207 with a half-life of 704 million years. By measuring the ratios of these isotopes in a mineral called zircon, which readily incorporates uranium when it crystallizes but almost never takes in lead, making it a near-perfect natural clock, scientists can determine with high precision exactly when that mineral formed. The oldest zircon crystals ever found on Earth date to roughly 4.4 billion years ago. They come from Western Australia, from a region called the Jack Hills. They are nearly as old as the planet itself. Grains of mineral the size of a sand particle have survived billions of years of geological upheaval, tectonic catastrophes, and erosion, preserving within themselves a record of their own birth. We read it through the lead isotopes inside. This is exactly how Patterson arrived at his figure of 4.55 billion years. Reading the age of the Earth through a dead metal that is itself a product of all that time. And now, the last thing, the widest view. Every atom of lead-206 in an ancient mineral is evidence that once, in that very place, there existed an atom of uranium-238, which lived out its allotted billions of years and arrived at this still inert point at the end of a long decay chain. A dead metal preserves the history of a living process. The final product carries within it the record of the entire journey that led here. In nuclear physics, there is a concept called magic numbers, specific quantities of protons and neutrons at which an atomic nucleus achieves exceptional stability. This follows directly from the quantum mechanical shell model of the nucleus. The numbers 82 and 126 are both magic. Lead-208 contains exactly 82 protons and exactly 126 neutrons, a doubly magic nucleus, one of the most stable isotopes among all the heavy elements. This is precisely why 3 of the 4 major natural radioactive decay chains end at isotopes of lead. It is a physically favorable, energetically stable state from which spontaneous further decay is simply not possible. Stars synthesize heavy elements in their cores and at the moment of their deaths. Neutron stars collide and scatter those elements into space. From this material, mixed with interstellar gas, new planets form. On planets, life appears. Life builds civilizations. And all the while, quietly, unstoppably, without reacting to anything happening around them, unstable heavy nuclei move towards stable configurations. Uranium-238 crawls toward lead-206 at the pace of 1 half-life every 4.47 billion years. Thorium-232 takes 14 billion years, roughly as long as the universe itself has existed, about 13.8 billion years. They are in no hurry. They have time. More time than we have words to describe it. But they are moving, always, only in one direction. Civilizations come and go. Rome stood for 12 centuries and collapsed, while its elite drank wine sweetened with lead acetate. The Industrial Revolution altered the chemical composition of the planet's atmosphere in roughly 200 years. One engineer from General Motors changed the chemistry of Earth's atmosphere twice and died without ever knowing the full scale of what he had done. One geochemist, with a clean room, a notebook, and an unbreakable refusal to be silenced, managed to measure it, prove it, and ultimately help stop part of it. And all that time, lead just sat there. In pipes, in paints, in batteries, in the aprons of radiologists, in hunting cartridges, in the bones of people who died 100 years ago, in the bones of people alive right now. Heavy, inert, gray, in no particular hurry. It has no reason to hurry. It's already where everything is heading. We think of ourselves as the pinnacle of something, of reason, of evolution, of civilization. But on the scale of nuclear physics, we are a temporary structure made of atoms, some of which are unstable. Radioactive isotopes in our bodies, potassium-40, carbon-14, are decaying right now, at this very second. Carbon-14 is becoming nitrogen-14. Potassium-40 is becoming partly argon-40, partly calcium-40. Quietly, without our knowledge, without our consent. We are made of matter scattered by cosmic catastrophes billions of years ago, and we ourselves are a temporary pause on the long journey of that matter toward equilibrium. Patterson understood this not in any philosophical sense, but in a strictly chemical one. He measured it, calculated it, and refused to be quiet. Against corporations with billion-dollar budgets and legal departments, against the inertia of an industrial system, against pressure on his funding and his reputation, one man with the right data, a clean room, and an unshakable willingness to speak the truth. Lead isn't going anywhere. It will remain in the soil along old roads, in the pipes beneath cities built in the last century, in the bones of people who lived through the era of leaded gasoline, in the walls of nuclear waste storage facilities that will stand for millennia to come. But at least there is less of it in our air. That is the only genuinely human outcome of this story. Not a victory over nature, not an alchemical triumph. Just one person who measured carefully, calculated correctly, and did not go quiet. The gray metal stayed gray. The heavy metal stayed heavy. The end point of decay chains stayed the end point. You can't argue with physics. But the air got a little cleaner, and that counts for something.